So it's time to give this basic Gauss elimination approach a run. So the first thing we do is we focus on the 2, 1 number. We need to set that location to 0 by performing row operations. The first row is the pivot row, so that's the one we will be scaling and subtracting from the second to make best use of things. So what do we need to scale the 4 by to be equivalent to -6? Negative 1.5 factor should take care of that. So negative 1.5 times, we'll just put that whole row in there. 4, -2, -3, 6. I'll just use square brackets to avoid some confusion. Equals negative 1.5 times 12. And so that would become -6 positive, just forego the plus, positive 3, negative 4.5, positive 9, nope, negative 9, positive 4.5, yep, got backwards myself, so, yep. Okay, and then negative 1.5 times 12, negative 18, make sure that sums up right, yep, that should work. Okay, so that is the scaled row 1. So now we need to subtract the scaled row 1 from row 2. So it'll be row 2 minus scaled row 1. Move that over so I actually have the right row. So row 2 would be -6 minus -6. So it'll be -6 minus a -6, so it'll be 0. 7 minus 3, 4, 6.5 minus 4.5, 2. -6 minus a -9 should be positive 3. And then -18 minus a -6.5. Excuse me, -6.5 minus a -18. Okay, that makes more sense. I keep on getting backwards. I think my notation was written down poorly. So this becomes the new scaled row 2. So now we need to rewrite the matrix, putting in this operation, putting in that row operation. So it becomes 4, -2, -3, 6, 0, 4, 2, 3. I should write out the solutions as well. 12. Unfortunately, rows 3 and 4 still require work. And in seeing this operation go through once, you start to see what we call this numerical methods and not do it at home for fun by hand methods. Okay, because rewriting that by hand would be horrible every time. Now you can do the same thing for row 3. You have to scale row 3, namely, looks like we're going to be multiplying it by 4 in a way that row 1 can be used to take it out. So or we can scale row 1, either way. So in this case, we'll take row 1 times a 4th and do R3 minus R1 to get that additional 0, focusing on that first column, third row location. I'm going to have to slow down to make sure I keep this notation proper. Okay, so the coefficient we need to multiply row 1, just write all these out. Coefficient we need to multiply row 1 by is 0.25, so that scales row 1, well, I'll just do it this way, R3 minus 0.25 R1 equals, you end up getting, thankfully, first coefficient of 0, second coefficient of 8, 7, 4, and then 13. So let's look at the first one. That makes sense because 4 times 0.25 is 1. If you're taking 1 minus 1, the high-level math tells you 0. R1, negative 2 times 0.25, that'd be negative 0.5. So 7.5 minus a negative 0.5 adds up to 8. All right, so that one checks out. Negative 3 times 0.25. Negative 0.75. Wanted to avoid making a mistake on the video, so I did actually have to chose to use a calculator for that one. Oops. So 6.25 minus a negative 0.75 takes you back up to 7. And then lastly, 6 times a solid 0.25, that'd be twice our previous entry, so that'd be positive 0.75. Twice, so positive 1.5. So you get 5.5 minus 1.5 takes you to 4. Okay, so that row operation is successful. Of course, performing the same thing on the solution, 12 times 0.25. You would get 3, so 16 minus 3 is 13. That shows that the row operation was performed correctly. This is the new row. We write it in. In fact, I am just going to erase this and save myself some suffering. 0, 8, 7, 4, and 13. Okay, last row, row 4. Working forward, what do we multiply row 1 by to equal negative 12? How about a negative 3? That should do it. So let's see here. Row 4 minus negative 3 times row 1. This gives us the coefficients. 0, 16, 6.5, 17, and the solution coefficient of 53. So we can just erase that row and override it with the new format. So all of these operations are really just subtraction. You're taking one equation, scaling it, which can be done freely as long as you scale both sides, and subtracting it from another. I mean, subtracting it, adding both directions, however you want to go. So that is the first column done. Oh my gosh. Now it's time to do the next one, next column. But thankfully, every column you do, you get to, it's one fewer operation. Okay, now we need to focus on eliminating this third row, second column location. We can't use row 1 anymore as the pivot. If we did, we would start reintroducing non-zero values in this leftmost column. We don't want to do any more changes to the column number 1. So we can use row 2. That conveniently, we just put a 0 there. So now our equations will be R3 minus some scaling of R2. So in this case, it looks like a scaling of 2 will allow us to eliminate things. Yep. So this ends up giving us the coefficients in the third row of 0, 3, negative 2, and negative 10. Again, just to keep things rather concise and clean, I'll erase what had existed. 0, 3, negative 2, negative 10. As you would expect, we're going to do the same exact thing for the fourth row. This gives us R4 minus the scaling here needs to be obviously 4 times row 2, which we're using as the pivot. Again, that R2 is the pivot row. This results in coefficients 0, negative 1.5, 5, and 7. Plugging it right into the matrix for that example. 0, negative 1.5, 5, and 7. All right, we're almost done. Last option, but again, we have to shift our pivot row because we do not want to disturb the nice zeros we have arranged in the first column and the second column. That form is good. We don't want to mess with it, so we actually move the pivot designation to be row 3. We are focusing our attention on just eliminating that last fourth row, third column entry. We need that to be 0, and then it is solved. It will be done. Well, it's at least in a form that we can say it would be done. Let's just eliminate all this. Erase real quick. Okay. R4. minus a scaling. Let's see here. What scaling could possibly make that work? How about we scale R3 by 0.5. 0.5 times R3 equals, that yields the coefficients 0, thank goodness, plus positive 4. I shouldn't say plus 4, but a 0, positive 4, and then the answer solution vector would be a 2. Erasing that last row with those numbers, 0, 4, 2. Oh my goodness, it's upper triangular. Thankfully. So if we think back about this being the general form of a system of equations, we now, eliminating all this R1, R2, R3, R4 stuff on the left, let's actually move this whole matrix back a little bit so I can squeeze in room for the unknowns, x1, x2, x3, x4. Alright, so if we set the first most challenging equation down at the bottom, it would be 0 times x1, 0 times x2, 0 times x3, and 4x4 equals 2. Therefore, x4 equals 2 divided by 4, also known as 0.5. So now we can go to the third equation. 0 times x1, 0 times x2, 3 times x3 minus 2 times x4 equals negative 10. Well, we know that x4 is 0.5, a positive 0.5. So negative 2 times 0.5, negative 1. Move that over, so we add a 1 there, that'd be negative 9. Negative 9 divided by 3, carrying that over. x3 equals negative 3. Collect our solution, just move it over here with its buddy. Okay. Now we know two of the answers. Let's keep going. Second row, 4 times x2 plus 2 times x3, which we already know. 2 times x3 would actually be a negative 6. Go ahead and do the math in advance. And then here we are, the third coefficient, 3 times x4. So 3 times 0.5 would be 1.5 plus 1.5 equals 11.5. So subtract off the 1.5, takes you down to 10. Adding in a 6 takes you up to 16. Dividing by 4 means that x2 equals 4. Alright, lastly we need to figure out what x1 is. So we have 4 times our last unknown x1 minus 2 times x2, so that'd be minus 8. Minus 3 times x3, so that'd be a positive 9. Plus 6 times 0.5, so it'll be a positive 3 equals 12. So 12 minus 3 would be 9. Minus 9 would be 0. Plus 8 would be 8. Divided by 4 would be x1 equals 2. Alright, so thankfully we finally have all 4 of the unknown variables. And confirming over here, yep, that worked out correctly. Let's actually go back and do this through MATLAB with the invert and multiply method. We taught you a little while back. So let's enter in the coefficient matrix from the very beginning. A equals 4, negative 2, negative 3, 6, semicolon for the next row, negative 6, 7, 6.5 minus 6, semicolon, 1, 7.5. I don't know why I'm reading all these to you. Reading them to myself, I suppose, so I don't mess these up. On entry, like that. A. Alright, so the solution vector B, have to enter that as well for good measure. 12, negative 6.5, 16, 17. 12, negative 6.5, 16, 17. Okay. A to the negative 1 times B equals roughly 2. 4, negative 3, and 0.5. So if we go back to our solution here, x1 was 2, x2 is 4, x3 is negative 3, x4 is 0.5. So we got it right. All that row manipulation by hand was horrid, but it's also very prone to mistakes, but it works out. And once a computer takes over those row manipulations, it can be done obviously much faster, much more precise. That's the whole point by going through this once by hand, so you understand the process and the reason we're chasing these upper or lower triangular matrices. That's the example.